Hello everyone. Today we'll talk about the solution to the problem minimum limit of balls in a bag. This is another case of what I call a staircase problem, where if we always look at the numbers that we're given, in this case the numbers of balls in every bag, and we look at it in decreasing order, we see a staircase because we have some big values and smaller, and we have some operations that allow us to take a step and do something with it. And we want to perform those operations and make sure that the top step after all those operations is as low as possible. So the total staircase is as low as possible. And typically in staircase problems like this, the two main approaches would be to either use simulation with a heap, because a heap is a method for us to in a pretty lightweight fashion, though still n log n fashion, maintain this staircase, or at least the size, the height of the highest step. And another, which is much more general and has the same time complexity of n log n, is binary search on the answer. And binary search on the answer, of course, is a pattern that happens. It is very general because it's a pattern for converting an optimization problem. So we want to minimize the penalty into a decision problem. Decision problem would be, is it possible for a penalty to be equal to, let's say, at most this value, and to still maintain the time complexity of the solution in a satisfactory manner. In this case, by adding binary search, we just add a logarithmic factor. We have to solve a logarithmic number of instances of the decision problem. And of course, the only case where we can use binary search on the answer is where there are some values for which it's possible to achieve them, and some values for which it's impossible to achieve them, and those two values are separated at some position, and everything is either to the one side of that position or to the other. It's either in the impossible side or the possible side, because that monotonicity allows us to use binary search. And so this will be the approach that we use, and we cannot use a heap here, both because in practice, when it comes to the constraints of this problem, it's impossible to perform a stupid simulation, right? A simulation without any smart optimizations, because here we have 10 to the 9 possible operations. But also, our operation depends not just on the original number of balls in every bag, but it forces us to perform a decision, because we have to split it into two positive values. And it might not be clear what split is the best at the point where we're making that split. And also there's the fact that the heap will be bigger and bigger, because essentially a split creates one new bag. So those are all problems, but all of those problems can be solved by binary search. That's because since we transform the problem into a decision problem, we know exactly how many splits we have to perform on a given bag, such that all the bags resulting from the split are below the threshold that we have set. So we'll be having the solution for our decision problem, which is just a simple function that I named bad. It returns true if it's impossible to reach the target without exceeding max operations. Otherwise it returns false, because it's possible to achieve that target. And now for every value v, we have to split that value maybe into some bags, such that all of the numbers of balls in those bags are below target, or at least not exceeding target, which means that the total number of balls that we have in this bag divided by our target is the number of balls that we have, or the number of bags that we have to make, right? So essentially, because in that case, so maybe in another way, we know that after we split in an optimal fashion, we will have the number of bags times the maximum value within any of those bags. This is the bound on what the number of balls in the original bag could be. And so we can just calculate it by a simple division, rounding up. We have to, of course, round up, because if we have one more ball, then one more ball has to go into one of those bags, and that bag, in this case, might exceed our target. So we divide v by target, rounding up, And to round up, we can divide rounding down, which is native in the language. And when you want to divide rounding down by target, but you want the result to be rounded up, you just add target but subtract 1. So v plus target minus 1 divided rounding down by target, this is just v divided by target rounded up. This is the number of bugs that we'll get at the end. And one bug we already have at the beginning, so we can subtract 1. And now notice that this decision of what the splits are, in this case, we don't have to worry about that decision. And if you want to explicitly think of that decision, it's just that since we want target to be the limit of the number of balls in any bug, then at every point where we split into one bug of exactly target balls, and all the other, so the original v minus target balls, stay in the same bug. We do not have to perform some weird like branching and binary trees. We can just take target at a time until the remaining value, so the v after all those operations, does not exceed target. And of course, if at any point for any of those values we get out of our limit of operations, so if the remaining operations is less than 0, we can return true. And now the binary search part, we can either write a normal binary search or write an open-ended binary search. So I start with 0. It's important to start with a value for which you're sure that the answer is that the case is bad. So for 0 is definitely bad, because we cannot even create, every bug has to have a positive number. And we'll be making jumps to the right for as long as it's still bad. And those jumps will start with some huge value, and whenever that huge value we see that it overjumps the correct position, we just divide it by 2 or shift it to the right by 1 when it comes to the bits. So this is the way of writing this open-ended binary search. While jump is greater than 0, again we'll be dividing it by 2 after every iteration. We want to take our current value plus jump and see if it's bad. If it's bad, then that means that, great, we've jumped over all of those other bad values, and now our bad value is much higher, and we can continue doing that, so that's why we have the while here. Typically, after the first time that jump gets divided by 2, this while will operate only once, so this is more of an if than while, but for it to be open-ended, so here I start with 10 to the 8, it's arbitrary what you put here, though it will change the runtime of your solution. But if the answer is 10 to the 9, then we'll have to make 9 or 10 jumps to reach that value. So while is safer here. And of course, if it's bad, our current value becomes that candidate. Otherwise, our current value doesn't change, but the jump gets smaller, gets divided by 2. And to write it in a concise fashion, we can use this walrus operator. So we run bad of cur plus jump, and this is our condition in the while. But we'll also remember cur plus jump as cand for us to here write that cur equals cand. And of course, at the end, we return cur plus 1. Why is it here plus 1? Because cur, after all those operations, is the highest value for which it's impossible to make the balls not exceed, it's impossible to ensure that every bug stays below that value of cur. So if we add one more to cur, then suddenly it becomes possible, and we're interested in exactly that, the smallest value for which it's possible. So we return cur plus 1.